Let's solve Unit 7 Data Structures and Algorithms questions. Which of the following descriptions are true? We'll start with red black tree. Guarantees worst case of O log n time for search, insert and delete. With red black trees, we can perform the following operations in big O of log n in worst case, where n is the number of nodes in the trees. What are the operations? Insertion, deletion, finding predecessor, successor, finding the minimum and maximum. Finding something is what we can equate to search. Insertion and deletion are given directly as insert and delete. So, big O of log n time is perfectly right. A statement is true. The next one, tries. They are used for efficient prefix-based searches. A trie is a tree and each node in it contains the number of pointers equal to the number of characters of the alphabet. This is much faster than hash table and binary search tree representations. Tries are especially efficient for prefix searches. This point is actually given in the question. So B statement is also true. What about C, AVL tree? It's a self-balancing binary search tree with stricter balance criteria. It's just a printing mistake, so it is stricter balance criteria. What is AVL tree? This is a binary search tree with a balance condition. The difference between left subtree height and right subtree height is at most 1. At most 1 means not greater than 1. It can be at the maximum only 1. So this at most 1 is what they state as stricter balance criteria here. We are actually given the term balance condition to denote this at most 1 difference. That's why here the term is stricter balance criteria. So based on the statement we can even mark C to be true. What about D, B tree? Allows efficient search, insert, delete operations in disk-based system. If access to each node requires a disk access, then a B tree will minimize the number of disk accesses required. So regarding B tree, it is actually for disk-based system. That's why they have given it allows efficient search, insert and delete operations. The minimization factor is usually chosen so that the total size of each node corresponds to a multiple of the block size of the underlying storage device. This choice simplifies and optimizes disk access. When they say it optimizes disk access or minimize the number of disk accesses, that is what we can equate to efficient search. Consequently, a B tree is an ideal data structure for situations where all data cannot reside in primary storage and accesses to secondary storage are comparatively expensive or time consuming. So definitely D is also true. If you take database management system, file organization topic, you can even find B tree content there. From this we can understand all the 4 statements are true, but at most we can find only A, B and D are given right here in 4th option. So this question has been officially dropped. It means there is no answer key provided. So if you want to get the answer, it will be option A, B, C, D. All the 4 statements are true. Next question, which of the following is not a divide and conquer method? So this is also one of the previous year questions. Sometimes the previous year question can have which is a method and sometimes it can be taken as which is not a method. So once you understand what are the applications of divide and conquer method, you should be able to answer which applications are not following this particular method. So let's see the divide and conquer applications. We have binary search, merge sort and quick sort, median finding, minimum and maximum finding, matrix multiplication and closest pair problem. We have binary search here, we have merge sort and quick sort. Heap sort is not available in this list, so we go with option number 4, heap sort as the right answer. This is not a divide and conquer method. Next question, which of the following uses only increment operations for adding and removing element at either end? Either end means when you take stack there is only one end. When you take queue there are 2 ends, front and rear. Similarly, when you take priority queue or DQ, there are actually two ends. So based on either end, we can say stack is definitely not a part of the solution. Now we will understand about every option. Queues follow first in first out FIFO principle. Add elements at the rear end and remove elements from the front is what we can say. So this is not allowing at either ends. So queue is also ruled out from the answer list. Let's see about stacks. Stacks follow the last in first out LIFO principle. Add and remove elements at one end, that is the top of the stack. We have already ruled out stacks. What about priority queues? Priority queues are not concerned with the order of insertion but rather with the priority of the elements. The element with the highest priority is removed first. So it is not about any end, it's just about the priority. So definitely 3 is also not the answer here. What about DQs? A DQ allows for insertion and deletion of elements at both ends of the data structure. This can be equated to either end, that is at both the front and the rear. This means you can efficiently add or remove elements from either end using only increment or decrement operations for the pointers that indicate the positions of the front and rear ends. So this particular statement is equating to the question statement, and so we are going with option number 4, DQs, as the right answer. As a learning part, what you can do is you can see how queues are implemented, stacks are implemented, priority queues and DQs are implemented. Just learn along with diagrams, understand how insertion deletions are happening so that it might be useful for you in some other question paper. Next question, considering the above binary tree, what will be the in-order traversal? What are the steps for in-order traversal? Visit all the nodes in the left subtree, visit the root node, visit all the nodes in the right subtree. So we'll start with left subtree. We don't have any left or right here, so we are selecting B first. So let's take this as right and this as left. This is root. So now left is done. What about the second step? We have to visit the root node. So we are considering A here. So this is also done. Now come to the right side. You have to move to the left side first. So when you go this way, this is left and this is right. So you have to pick the left element here, which is D. So D will be here. Then you have to pick up the root for this particular left and right. So this is C. Now again get to the right side. For this particular subtree, you don't have left here, but you have the root node. So you have to include E here. This is actually the right side of the E node. So for right subtree, again you have to go with left, right, root. So what is left here? It is G. What is root? It is F. What is the right? It is H. This is how you have to do in-order traversal. B, A, D, C, E, G, F, H. This is available in option number 1. If you are not able to traverse in the same diagram, just take A, B, C. This is left, this is right, and this is the root node you can take. You go with B, A. For C, what you can do? You can take C here and go with D and E separately. Take only D and C, cut off E from here. Take the E subtree separately. E, F, it is given here. So here you have no left and only the root is there. So mention the root. After the root only you are going to process the right side. So cut this part. Again go for F. F has a left child and a right child. What is the in-order traversal? It is G, F, H. So this order will be given as it is. This is how you have to split and do for a big tree. Let's see the other options. G, H, F. So they are starting with this particular tree. Actually we have to not get inside the right part. So option 2 can be ruled out. If you take B, A and C, they have started with left, root and right. This might be correct if C does not have any child. But C has left and right children. So definitely this order cannot be taken. So 3 is also ruled out. Again it is starting with GHF, so we can rule out. Next question, which of the following is the solution of the following recurrence relation? So we have already solved few recurrence relations in the previous year question paper. We will take the Master's theorem. This particular Master's theorem is in the form of T of n is equal to A into T n by B plus f of n, and this Master's theorem is in the form of C into n power d in the place of f of n. So you can either refer to this Master's theorem or this Master's theorem, but here it is given in the form of big O only, but here it is with respect to big O, theta and omega. The Master theorem states that for a recurrence of the form T of n is equal to A into T n by B plus f of n. The number of subproblems is denoted by A and the factor by which the problem size is divided is given by B. What about f of n that comes outside here? This is the work done outside the recursive calls. So whatever happens in between A into T of n by B is about recursion, and whatever is given along with the recursive call is the work that is done outside the recursive calls. Let's take the given recurrence relation T of 2 into n by 3 plus 1. Do we have any A term here? A can be equated to 1 because 1 into something is going to give that something only. What about the B value? In the general form it is given as T of n by B. B is given in the denominator. When you have a fraction in the denominator of the fraction will go to the numerator. Say for example, if you have n divided by 3 by 2, this can be written as 2 into n by 3. So you have to understand this form is rewritten in this way. So what is B here? It is 3 divided by 2 and not 2 divided by 3. So we have A is equal to 1 and B is equal to 3 divided by 2. So what is n power d here? It is given as 1. Say for example, n power 0 can be taken as 1. This n power d can be equated to n power 0, which is equal to 1. This is the f of n part as per this particular formula. So here we can equate d is equal to 0. Now we have to check a and b power d. A is equal to 1. What is b power d? This is also equal to 1. From this what we can understand, a is equal to b power d. So we are going with the second part. So this is giving big O of n power d log n. What is n power d? It is n power 0. What is log n? We have it as it is. So what is n power 0? It is 1. 1 into log n will give you big O of log n. So here they have given with respect to big O, but here it is given in form of theta. I will tell you how it is equated. So right now we have to understand log n is the complexity. So we will go with option number 2 as the right answer. Now let me solve with this particular part. We can interpret n by b to mean either n divided by b under floor or n divided by b under seal. Then T of n has the following asymptotic bounds. They have given theta everywhere, so we will pick up this one. So we will go with theta of n log ba. So this particular part is taken to be 0. Only n power 0 will give you 1 in this particular place. From this we can infer log a to the base b is equal to 0. Now just apply here. This is theta of n log ba log n. This is T of n is equal to. So from this theta of what is log a to the base b? It is n power 0 log n. From this we can say it is theta of log n. So we are going with option 2 as the right answer. So whether you take it this way or this way, you should be able to apply the power and get it properly. Next question. Arrange the following steps of the in-order traversal of binary tree in the correct order. Visit the left subtree, visit the root node, visit the right subtree. Start traversing by visiting the nodes in rooted tree. Repeat the above 3 steps. They have given the clue here, start traversing. So we have to start with D. We can rule out option 1 and 2. Then we have to get into the traversal. Left, root and right. So A, B, C. A, B, C is given here. So we can rule out even option 4. What about E? Repeat the above 3 steps. So if you take B, then A, then C, here you can stop within these 3 nodes. But when you have subtree here, you have to go for repeat. So we are starting, going for the traversal and then repeating the process again. D, A, B, C, E is available in option 3. Option 3 will be the right answer. Next question. Which of the following algorithms are based on the breadth first search? When you take breadth first search application, Dijkstra's algorithm will have a direct application. Dijkstra's algorithm is a generalization of the breadth first search algorithm. This point is actually given in many of the books. So we know definitely C is in the answer. Any option that does not include C can be ruled out. So from this we can say Kruskal is not there and dynamic programming is also not there. Dijkstra's algorithm uses a priority queue to efficiently find the shortest path from the source vertex to all other vertices in a weighted graph. It can be thought of as a weighted version of BFS. So this is definitely there and this is C. What about Prim's algorithm? In Prim's algorithm, priority queue is used to efficiently select the edge with the smallest weight that connects a vertex in the minimum spanning tree to a vertex outside the minimum spanning tree. It is somewhat similar to how BFS explores the nearest nodes first. Prim's algorithm does not have a direct application of BFS, but they say the way it selects the edges is similar to how BFS explores the nearest nodes first. So this can also be included. So A is definitely there. Now we have to check whether D is included or not. Greedy algorithm. This approach makes a series of choices by picking the best available option at every step, aiming to find a local optimum with the hope of finding a global optimum. Prim's algorithm and Dijkstra's algorithm, they use a priority queue to start with a shortest path in case of Dijkstra's and to select the edge with the smallest weight in case of Prim. But in greedy algorithm, we are not going with such criteria. Instead, we are just taking the best one available at every step. So in that way, greedy is not connected to Dijkstra's and Prim's. So we are removing even greedy algorithms from the answer list. So 2 is also ruled out. Option number 4, A and C only will be the right answer. What about dynamic programming? A method for solving complex problems by breaking them down into simpler subproblems and storing the results of subproblems to avoid redundant computations. This is nowhere related to BFS, so we are ruling out dynamic programming. What about Kruskal's algorithm? This algorithm follows a greedy strategy through its approach of always picking the smallest edge that does not form a cycle. So Kruskal algorithm is also to find minimum spanning tree. But how does it pick? It will pick the best available option at every step. What is best available option? Whichever edge that is smaller and that does not contribute to a cycle will be picked up. So this is following greedy strategy. Next question, choose the correct statements. A problem which is NP complete will have the property that it can be solved in polynomial time if and only if all other NP complete problems can also be solved in polynomial time. All NP complete problems are NP hard problems. If an NP hard problem can be solved in polynomial time, then all NP complete problem can be solved in polynomial time. All NP hard problems are not NP complete. This is the diagram that we know about NP, NP hard and NP complete. From this diagram, what you can understand is NP complete problem is an intersection of NP and NP hard. NP hard does not have a closed bound. It is open. Just check this statement. All NP hard problems are not NP complete is perfectly true. Just take for an example, NP complete has a count of 10 problems. Since NP hard is given in open end, it will have some 20 or 30 problems, but definitely more than 10. So they are saying all 30 problems are not NP complete problems, which is perfectly true. So D is definitely true. All NP complete problem are NP hard problems is what B statement is telling. If you take this particular 10 problem, it is a part of NP complete. At the same time, it is a part of NP hard problem too. So all NP complete problem are definitely NP hard problems because NP complete is intersection of NP and NP hard. So B is also right. NP complete problems are a subset of NP hard problems that are both in NP and NP hard. Not all NP hard problems are NP complete. This point is what they have rewritten in statement D. All NP hard are not NP complete is equal to not all NP hard are NP complete. So both are same. Any NP complete problem can be reduced to any other NP complete problem in polynomial time. If one NP complete problem can be solved in polynomial time, all NP complete problems can be solved in polynomial time due to this polynomial time reduction property. A problem which is NP complete will have the property that it can be solved in polynomial time if and only if all other NP complete problems can also be solved in polynomial time is what this statement is also saying. So A is also true. This particular statement will state that both B and D are true. Similarly, this particular point will state that A is true. If an NP hard problem can be solved in polynomial time, it implies that there is a polynomial time algorithm for the hardest problems in NP. Just check with C. If an NP hard problem can be solved in polynomial time, then all NP complete problem can be solved in polynomial time. So the subset of NP hard is NP complete. So definitely C is also right. You can take these 2 points into consideration to say C is true. So we know NP complete is a subset of NP hard. When you have an algorithm to solve them, definitely this can also be solved in polynomial time. All the 4 statements are true. So we are going with option number 4, A, B, C, D as the right answer. Next question. Match the list 1 with list 2. List 1 has search and sort algorithm. List 2 has complexity. Let's start with binary search. A search algorithm that finds the position of a target value within a sorted array by repeatedly dividing the search interval in half. If there are going to be n elements, you are going to consider only n by 2 elements at a time, which is going to have the complexity of big O of log n. B will be mapping to 1. B1 is available only in one option. We will go with option number 1 as the right answer. What about insertion sort? This is a simple sorting algorithm that builds the final sorted array one item at a time by repeatedly taking the next item and inserting it into its correct position. The time complexity is given as big O of n square on average and worst case and big O of n in the best case when the array is already sorted. Quick sort. A highly efficient sorting algorithm that uses a divide and conquer approach to partition the array into subarrays which are then sorted independently. The time complexity will be big O of n log n on average but big O of n square in the worst case when the pivot is poorly chosen. We usually choose the leftmost element as the pivot element. But here they say when the pivot element is poorly chosen, it can result in big O of n square in the worst case. Otherwise, this has a complexity of big O of n log n. What about selection sort? A simple comparison based sorting algorithm that repeatedly selects the smallest or largest element from the unsorted portion of the array and moves it to the beginning or end. So if it is smallest, it will be moved to the beginning. When you choose the largest, it moves to the end. You have to apply it in this way. The time complexity is big O of n square in all cases. So D will be mapping to 2 in all cases. What about quicksort? We have n log n. So C will be mapping to 4. What about A3? So just take this to be big O of n. So A will be mapping to 3 here. A3, B1, C4, D2 will be the right answer. Next question. Match the list 1 with list 2. We have breadth first search, depth first search, prefix, infix in list 1, Lisp, it's a programming language, syntax tree, stack and queue in list 2. BFS uses a queue to keep track of the nodes to be explored. It explores all nodes at the present depth level before moving on to nodes at the next level. So BFS is going to use queue. A will be mapping to 4. What about DFS? Depth first search can be implemented using a stack, either explicitly with a stack data structure or implicitly with the call stack during recursion. It explores as far down a branch as possible before backtracking. B is mapping to 3. A4, B3 is available only in one option. We can rule out the other 3 options. Option number 4 will be the right answer. Prefix notation, which is also called as polish notation, is commonly used in Lisp, list processing, which is a programming language. What about infix? Infix notation can be represented using a syntax tree, which is a hierarchical structure that represents the syntactic structure of expressions based on grammar rules. This is postfix and this is prefix. What is infix? It is A plus B. Prefix C will be mapping to 1 Lisp and D infix is mapping to 2 syntax tree. A4, B3, C1, D2 will be the right answer. With this, we are completing Unit 7 solutions.